Hello friends, welcome back to my channel. In this video, I am going to solve exercise question from book Topics in Algebra from chapter 4 Vector Spaces and Modules. Question is, if V is of dimension n, show that any set of n linearly independent vectors in V forms a basis of V. Before proving this given result, firstly we will recall definition of basis of a vector space. So, a subset B of a vector space V is called a basis of V if B consists of linearly independent vectors and V is equal to linear span of B. So, proof: here V over field F is a finite dimensional vector space of dimension n. Now, let us consider set B, which is a subset of vector space V consisting of n linearly independent vectors, say u1, u2 up to so on un. Now our claim is to show that this set B is a basis of vector space V. Further, note that if V over field F is a vector space, then V is said to be finite dimensional if there exists a finite subset, say S, of vector space V such that V is equal to linear span of S. Now from this concept, it is sufficient to show that vector space V is linear span of the set B. That is, to show every vector in V can be expressed as a linear combination of vectors in set B. Next, we have one theorem which states that let V is finite dimensional vector space with dimension of V is equal to n, then any subset of V which contains more than n vectors is always linearly dependent. Next, consider any arbitrary vector, say u, in vector space V. Then by above theorem, the set containing vectors u, u1, u2 up to so on un, that is the set containing these n plus 1 vectors, is always linearly dependent. Now, claim is to show that vector u is a linear combination of the n vectors u1, u2 up to so on un. Now note that as this set u, u1, u2 up to so on un is linearly dependent, so there exist scalars, say alpha, alpha 1, alpha 2 up to so on alpha n, not all 0, such that the linear combination alpha u plus alpha 1 u1 plus alpha 2 u2 plus and so on plus alpha n un is equal to 0. Now we have two cases. Case 1, if the scalar alpha is equal to 0, then from this linear combination we can write the linear combination alpha 1 u1 plus alpha 2 u2 plus and so on plus alpha n un is equal to 0 with some alpha I not equal to 0. But this is not possible as all the ui's are linearly independent. So this case fails. Next case is case 2. If we consider the scalar alpha is not equal to 0, then from this linear combination we can write alpha u is equal to minus of alpha 1 u1 minus alpha 2 u2 minus up to so on minus alpha n un. Now since this alpha is not equal to 0, we can write this as u is equal to minus alpha 1 divided by alpha u1 minus alpha 2 divided by alpha u2 minus up to so on minus alpha n divided by alpha un. This implies u can be written as beta 1 u1 plus beta 2 u2 plus and so on plus beta n un, where each beta I is equal to minus of alpha I divided by alpha is some scalar in field F. Now from here we can say u is a linear combination of these n vectors u1, u2 up to so on un, and therefore u belongs to linear span of set B. Now as u is any arbitrary vector in vector space V, we can assume that, or we can conclude that vector space V is equal to linear span of the set B, and therefore the set B consisting of n linearly independent vectors u1, u2 up to so on un becomes a basis of vector space V, and this proves our result.